Hello and welcome. My name is John Horvath, and my presentation today is about reconstruction of a section of US Route 30 that follows a section of the historic Old Oregon Trail in Idaho. This is an interesting case history. It was the first time that the Iowa Transportation Department used EPS-Block Geofoam as a primary material in a transportation earthwork. And this project has been in service for about a decade now, so we have the opportunity to see how this material performed. There are actually some interesting innovations with the use of geofoam on this project. I've divided my presentation into segments. This is both to present it in an orderly fashion as well as to facilitate viewing by you, the viewer. You may find it advantageous to break up your viewing into segments to fit the time that you have available. Before I get into my presentation today, I'd like to point out that I presume that you, the viewer, has a basic working knowledge of how block molded expanded polystyrene, what we call EPS block, is manufactured, the basics of its material behavior, and a knowledge of the standards that are applicable to its use as a small strain geofoam function of lightweight fill. If you're not familiar with these aspects, or if you would like to refresh your knowledge or to increase your knowledge, I strongly suggest that you, before viewing this presentation, that you view another one of my presentations that you can find on my YouTube channel that deals with, it's a primer on the material behavior of EPS as a geofoam material. So you may want to go view that primer presentation first, or if you already have some basic knowledge, please continue on with this presentation. A bit of a background about the project. The project site is located within the southeast corner of the state of Idaho. Pocatello is the largest major city to the site. Located within Bannock County, and specifically a section of US Route 30 between McCammon and Lava Hot Springs. This is a very significant US highway to a certain extent. It carries a lot of traffic similar to an interstate highway in a rural area. So there's a lot of commercial traffic on this road. The nearest municipality to the site is a small development called Topaz. So the project is officially known as the Topaz Bridge Project. A bit of geotechnical engineering history. The Topaz Bridge Project site is quite close to the infamous Teton Dam site. And geotechnical engineers are familiar with the infamous Teton Dam failure not all that many years ago. This was a failure of an earth embankment dam fairly soon after construction as was being filled. And because the failure occurred in daylight over a period of several hours, it was well documented at the time, both in still photographs as well as videographs. As you could see, it was a complete and total catastrophic failure. They never rebuilt the Teton Dam. In fact, to the present, the Teton River runs through the site of the Teton Dam, and as you could see, there are remnants. The spillway, as well as part of the failed embankment, have simply been left to nature. But we're here today to talk about certainly one of our more positive geotechnical accomplishments, and that's the use of EPS block geofoam on reconstruction of the Topaz Bridge. The Topaz Bridge project site lies along the route of the historic Old Oregon Trail, which was a major land route between the Midwest gateways of St. Louis and other cities and the Pacific Northwest. And even though wagons and trails have given over to railroads and highways, both the railroads and the highways follow this same route at the present time. So this is still a major transportation corridor to and from the Pacific Northwest. If we move up to around 1940, we find that US Route 30N traversed through the Topaz area along the route of the Oregon Trail. Here we see the very small development of Topaz, which was a small station on the Union Pacific Railroad. This, in the past and at the present, is a significant main line for the Union Pacific Railroad, as I said, to and from the Pacific Northwest. Other prominent features in the area and in this project are the Portneuf River. The Portneuf River runs from east to west through this area. And also of significant note is the beginning of the Portneuf Marsh Valley Irrigation Canal. This canal was an early 20th century development, and as we'll see, the canal begins within the Topaz Bridge site. And this is the future site of the Topaz Bridge. So the original U.S. highway through this area that followed the route of the Oregon Trail did not cross the Portneuf River in this area. As you could see, there was no Topaz Bridge circa 1940. Here are some historical photographs through the area. We see that the Portneuf River Valley is, for the most part, a fairly wide, flat valley, very classic meandering river type valley. There are mountains both to the south and the north, and you could see that the circa 1940 US Highway 30N was fairly typical of that area. Certainly is what was called an improved road in that it had a pavement wearing course, but it was certainly a relatively crude road by today's standards. In the late 1940s, right after the end of World War II, there was a decision to relocate a section of US Highway 30N, beginning on the west at this yellow asterisk and continuing to the right beyond the limits of this particular map. And as we see, the site of the future Topaz Bridge was just to the east of the beginning of this relocation. So this late 1940s relocation essentially moved the highway from the north edge of the valley to the south edge. And in this photo here, it moved the highway from left to right. So the original US Route 30N traversed the northern edge of the valley, the foothills of the mountains to the north, and the relocated US Highway 30 traversed the southern edge of this valley along the mountains to the south. These are some historic photos during the relocation effort. The embankments for the relocated road were constructed using native soils, which are predominantly fine grained in nature. So you see the use of a sheep's foot roller, which is then and now not uncommon when you have fine grained soils. Because the relocated road would have to cross the Portneuf River, the decision was made to channelize the river through corrugated metal culverts. And we'll see why, because keep in mind, by the time the highway was relocated in the 1940s, the Portneuf Marsh Valley Irrigation Canal already existed. So this just shows the installation of corrugated metal culverts with poured in place Portland cement concrete head walls to allow the embankment for the relocated highway to cross the Portneuf River Channel. A significant feature of the relocation was the so-called Topaz Bridge. The Topaz Bridge was a 5-span structure. The center span was a truss bridge, quite typical of the era, and that spanned over what was then the double-track main line of the Union Pacific Railroad. I like to call the original Topaz Bridge a bridge over a bridge, because at the exact same location that the relocated U.S. Highway 30 crossed the railroad crossed over the Portneuf Marsh Valley Irrigation Canal. So you don't see it very well in this photo, but the railroad here is on a bridge crossing the canal. This is a view to the east from the west approach embankment to the to the Topaz Bridge. The west approach embankment will figure very prominently, in fact, is the focus of this presentation. And we see this was certainly an improvement over the original highway, but it was a 2-lane highway with minimal shoulders. Looking at a map of the area, we see that the Portneuf River is a very classical meandering river. We see remnants, Oxbow Lake, remnants of prior channels of the Portneuf River. And we see that the Portneuf Marsh Valley Irrigation Canal begins right up here. These two colored asterisks mark the beginning and the end of the 1940s relocation of U.S. Highway 30N to U.S. Highway 30 through the area. And again, this relocation is what caused the construction of the original Topaz Bridge. By the way, the original alignment of U.S. Highway 30N still exists. It is now appropriately labeled Old Oregon Trail Road. So the original U.S. Highway 30N still traverses through the area. This is an aerial photograph from circa 2010, just before the project history, case history I'm going to discuss today. And this red asterisk here is the same location as here. We see the Portneuf River. We see the Portneuf Marsh Valley Irrigation Canal. The canal begins right around here. We'll see in some later slides there are a number of diversion flow control structures. So this is the beginning of the canal, and you see the canal is actually wider than the Portneuf River through this area, which is why when they built this embankment in the late 1940s, they were able to channelize the river through culverts through the embankment as opposed to a bridge. So here we see the canal, and we see the bridge over bridge type of feature. Here is US Route 30. Here's the railroad, and here's the canal. So this was the original alignment of US Route 30N prior to the late 1940s, and this is now the relocated alignment. And again, this is the point of diversion, corresponds to the same point we see here. This is the original Topaz Bridge, crossing over the railroad, which crosses over the canal. And this is the west approach embankment that, as I said, is really the feature of this case history discussion. This was really the remarkable aspects of this project that was undertaken about a decade ago. These are some additional photographs from around 2010, just before the project I'm going to discuss today. This is a view from the west approach embankment toward the east. Again, we see the railroad here. Here's the Portneuf River, and this is the west approach embankment that features prominently in my presentation today. Fairly steep sides, about 1.5 horizontal to 1. You could see that the Idaho Transportation Department has had trouble over the years trying to keep the embankment stable against erosion. This area in Idaho does not get a lot of rainfall precipitation. It gets approximately 12 inches, 1 foot of rainfall per year. So about 300 millimeters of rainfall. And that's about 1/3 the average rainfall in the United States. The area does get a fairly significant amount of snow, approximately 4 feet of snow on average, so somewhat greater than 1 meter of snowfall per year. But all in all, this is a fairly dry area, and most of the farming that is done in this part of Idaho is what they call wet farming, which requires irrigation during the growing season. But we see a nice view of how wide, in general, the Portneuf River Valley is. We have mountains to the north, mountains to the south, but through most of this area, the Portneuf River Valley is fairly wide. And again, that's fairly typical of meandering river valleys. We will see later on that the Portneuf River Valley is quite narrow through the area of the West Embankment, and this has really created some geotechnical problems that were central features of the project I'm going to discuss. This is just another view to the southeast, taken from the original US Highway 30N, the old Oregon Trail, looking at the 5-span original Topaz Bridge from the 1940s. Again, we see the characteristic truss center span. These are a couple of views, again, taken circa 2010, just prior to the project I'm going to discuss today, from the West Approach Embankment. And this red asterisk corresponds to the red asterisk I showed you on some earlier slides. This marks the beginning of the relocation project in the late 1940s. The original Oregon Trail and US Highway 30N goes off to the left here toward the north. Now, you can see the lettering on this annotation, but what the photographer was pointing out is that there are, on this West Approach Embankment, just prior to the project I'm going to discuss today, there were 2 significant dips in the roadways with cracks in the asphaltic concrete wearing coarse pavement. One was about halfway down the West Approach Embankment, and the other was just prior to the beginning of the Topaz Bridge. And this is a close-up. This photo doesn't do justice to it. You have a very significant, this is the closer dip in the roadway. There's a very pronounced dip, was a very pronounced dip in the roadway, and you can see there's a crack running the full width of the top of the highway embankment. So clearly, the road, which at that point had been in existence for something in excess of 40 years, nature was telling the engineers that there were some geotechnical issues going on here with respect to total and differential settlements that needed to be recognized during the reconstruction. So by the early 2000s, the ITD, the Idaho Transportation Department, recognized that the Topaz Bridge was structurally inadequate and functionally obsolete. Again, it only had 2 lanes with minimal shoulders. And as I said, this was a highway that sees a substantial amount of commercial traffic. And by that, we're talking trailer trucks, what in other English-speaking countries you call articulated lorries or artics. So there was a desire to widen US Route 30 between McCammon and Lava Hot Springs, and the ITD wanted to accommodate 2 traffic lanes plus a breakdown lane in each direction. And that was to better handle both the current as well as projected traffic volumes. Concomitant with that was the desire to reinstall a second track for the Union Pacific Railroad, as this is a major intermodal route to and from the Pacific Northwest. As you saw in an earlier photograph, this had once been a double track route, but the railroad had to single track it to provide for greater clearances beneath the existing Topaz Bridge, both vertical and horizontal clearances, to account for intermodal traffic, what is sometimes called double stack traffic, where they stack one trailer on top of another. So the constraints of the existing Topaz Bridge did not allow the railroad room to add a second track with modern clearances. So the decision was made for a variety of reasons to replace the Topaz Bridge and widen the roadway to a total of 4 traffic lanes plus a breakdown lane in each direction. Essentially, what was decided was that a 2-lane road with very narrow shoulders had to essentially be transformed into a 6-lane roadway. So this was quite a significant reconstruction. It was not a simple rebuilding to the same parameters that existed. This was a very substantial increase in the number of lanes of the roadway. In this next segment, I'm going to go through an overview of really the design issues that drove the design of this project. Really form a background for why the project was designed the way it was. So the proposed Topaz Bridge replacement and widening, roadway widening had quite a few significant technical issues as well as logistical constraints. So it wasn't just a simple improvement project of rebuilding in kind. The overall site is quite remote. This is a fairly remote area in Idaho. It's approximately 1 mile, so about 1,500 meters above sea level in elevation, and is subject to severe sub-freezing winter weather. As I already noted, they do get a significant amount of snowfall, approximately 4 feet, somewhat over a meter worth of snowfall every year. So there were a lot of aspects of construction, materials, logistics that really had to be planned and thought out around these considerations. Another significant requirement is that 2-way road traffic had to be maintained at all times. As I've said, this route has considerable commercial traffic, and given the remoteness of the area, there was no reasonable detour. Certainly it was not feasible to send traffic through the original US Route 30N. This road simply could not accommodate that type of detour. So among other things, what it meant is that the replacement bridge wasn't just a single bridge. It had to be built as 2 separate parallel bridges, but later connected to function as what amounted to as a single 6-lane right-of-way. In addition, the rail traffic had to be maintained more or less at all times. Again, this was a very significant main line of the Union Pacific Railroad, and although the railroad could accommodate some short closure windows, certainly a shutdown was not feasible. In order to provide more clearances for the railroad, both vertical and horizontal, the final roadway surface at the bridge location had to be higher by several feet, a couple of meters, compared to the existing roadway surface. And this was especially true because the design alternative for the replacement bridge was not a truss, but a deep plate girder. So they did not replace the bridge with the same type of bridge. They went with a deep plate girder bridge. So they had to provide additional clearance on the underside of the plate girder. So as we'll see, the roadway surface, the new roadway surface was quite a bit higher than the original surface. Also needed to have more horizontal clearance of the rail right of way. Another significant consideration is that there's an extreme skew angle, very acute skew angle between the roadway and the railroad. And this meant that the clear span, you put all these things together, the clear span of the new replacement bridge was much, much longer than if you just had a simple orthogonal crossing. And, you know, as we know in structural engineering, bending moments as a first order approximation vary as span length squared. So this meant that very substantial deep plate girder in order to carry the design loads. And we'll see this in subsequent photographs. This just shows the pre-construction aerial view circa 2010. And again, you see between the railroad and the US Route 30, this is a very, very acute angle of this crossing. So this meant that the clear span over the railroad had to be required a much, much longer clear span than if the highway and the railroad simply crossed at 90-degree angles or something closer to 90 degrees. Well, the bottom line is that the approach embankments on either side needed to be raised several feet, a couple of meters, as well as widened to accommodate the new roadway geometry. So it wasn't just the bridge that was a challenge. There were challenges, as we'll see, with the approach embankments. The west approach embankment is quite long, as we'll see, and all this widening and raising had to be constrained to more or less the existing right-of-way limits. So in very simple terms, they had to stay within the existing toe slope of the existing highway due to environmental constraints, because you had wetlands adjacent to the Portneuf River and the Portneuf Marsh Valley Irrigation Canal. So again, here's the original Topaz bridge that had to be replaced, and here is the west approach embankment, quite long. And we could see that there are wetlands on either side, so there was quite a bit of constraint in terms of what could be done horizontally to both raise and widen this west approach embankment. As we'll see, the east approach embankment was trivial. There really were no significant issues there. Put all these design considerations together, and it meant that the new west approach embankment had to have vertical faces along both the north and south sides. We could not have sloped sides as with the existing embankment. The reason that the west approach embankment really is what drove this project from a geotechnical perspective is that it crossed a deceptively wide meander valley of the Portneuf River. As I'll show you in some slides in a minute, the Portneuf River Valley was quite narrow at the actual bridge location, and over the millennia, the wandering Portneuf River had eroded a relatively deep, steep wall depression within the underlying basalt bedrock. And this depression, this meander valley, had been filled over the millennia with fine-grained soils that were quite compressible and relatively weak. On the other hand, the basalt bedrock was actually at the actual bridge location was relatively shallow, and certainly was shallow beneath the relatively short east approach embankment as well. So all of the geotechnical issues really were involved the west approach embankment. Not to trivialize the bridge foundations or the east approach embankment, but these did not present any inordinate unusual challenges. This gives you I'll show you a couple maps that show you in more detail what I'm talking about. Here we see the US Route 30 alignment. The contours on this map are in feet, so 5,200 feet. We see this is a mile or so above sea level. Again, we see relatively steep mountains to the north and south of the Port-Neuf River Valley. Through much of this area, the Port-Neuf River Valley is relatively wide, but we see that as we get to the Topaz Bridge site, the valley narrows rather significantly. See, there's not too much horizontal distance between these two mountains. So while throughout much of the valley, the Port-Neuf River is meandered over the millennia, as you could see from the Oxbow Lakes, it's been constrained quite a bit at this location, so eroded a relatively deep valley. Looking at things in a little bit more detail, and this contour map is in meters, so this is 1,500 meters, so again, just about a mile above sea level in elevation. Here we see that the east approach embankment is really at the foot of this mountain, so rock was relatively shallow. There were no fine-grained soils to create problems. Here we see the railroad and the Topaz Bridge are here, again at the foot of this mountain to the south, so bedrock was relatively shallow. Foundations for the new bridge were drilled shafts, did not present any unusual or extraordinary challenges. But we see that the west approach embankment traverses this relatively narrow valley that is surprisingly deep, several tens of feet deep, several meters deep, and filled completely with fine-grained soil that presented challenges with strength and compressibility. Again, we see here the original alignment of US Route 30N avoided this whole problem area. That's because it skirted the foothills of the mountains to the north. So this is the original route, US 30N, the original route of the Oregon Trail. So the point I'm making here is that for the west approach embankment, settlement, total and differential, as well as shear strength, and both of these as a function of time as a result of any new fill placement. And because the embankment on the west side had to have a vertical face, that would have required some type of earth retaining structure to retain the new fill. These were all major design and construction issues, and also long-term operation and maintenance issues. This final operation and maintenance aspect was certainly supported by observing the existing west approach embankment that had been in service for roughly 40 years, that exhibited multiple areas where the roadway surface had differential settlements and very noticeable cracks in the pavements. And again, this was the slides I showed you previously, that this is the west approach embankment, going from shallow bedrock to deep bedrock, and the transition from shallow to deep and then back to shallow bedrock was in the borings that were drilled for this project were almost vertical cliffs below ground, almost vertical faces in this valley. So there were very, very abrupt transitions from shallow rock, deep rock, and back to shallow rock as you traversed along the alignment of this road. So the bridge itself, the rock was shallow, and certainly the east approach embankment on the other side, the rock was shallow. But along this side, the rock was surprisingly deep. So again, as I pointed out earlier, this existing roadway that had been in service for about 40 years was basically telling the design engineers, hey, look, there are geotechnical problems in this area. Well, just to add to things, to make life interesting, the site has a very significant seismic potential. So that meant that all the project components, the bridge as well as the approach embankments, had to be designed for seismic loading. This is the U.S. Geological Survey seismic hazard map for the United States, issued in 2018. And here is the Topaz Bridge site. And you can see that it is well within this band of relatively high hazard. Okay. Obviously, here we have the west coast of the United States, Southern California, Pacific Northwest. These are well-known, very significant hazards. Here we see the central U.S. around the New Madrid earthquake zone, Charleston, South Carolina, certainly Alaska, parts of the Hawaiian Islands. But compared to much of the continental United States, this is a very significant seismic zone. And just to orient yourself, here is Yellowstone National Park up here in the northwest corner of the state of Wyoming. And this is where you have Old Faithful and all those geysers. So this is an area that has a lot of tectonic activity going on. Magma close to the surface, creating these natural geysers. And certainly there's a well-proven history of significant earthquakes. The famous or infamous Hebgen Lake earthquake of 1959 that caused quite a bit of human fatality and damage and literally created a new lake that's called Quake Lake. Had a moment magnitude of 7.2. That was located epicentered in this same band of high seismic activity that extends from south central Montana through western Wyoming, the southeast corner of Idaho, and down into Utah, into the Salt Lake City, Ogden area down here. Well, the remainder of my presentation is going to focus on the widening and raising of the West Approach Embankment. This is really, not only did it contain all the geotechnical challenges of the project, it's really where the most innovative and complex design and construction elements of the project existed. As I said, the drilled shafts for the new Topaz Bridge, the raising of the East Approach Embankment, these were all straightforward geotechnical and foundation and engineering challenges. Really, all the really significant challenges were for the West Approach Embankment. Having discussed the overview of the technical and logistical issues that really drove this project, I now want to talk about the specific design choices that were made with respect to the West Approach Embankment. I've divided this segment up into several topics to, again, present the material in a logical fashion, as well as to facilitate your viewing. An overview of the design concept. The overall project called for the existing roadway alignment, two-lane roadway alignment, to essentially become the new eastbound travel and breakdown lanes. So that meant that all the roadway widening for the new westbound travel and breakdown lanes would occur to the north of the existing roadway and existing West Approach Embankment in the direction towards a wetland area between the Portneuf River and Portneuf Marsh Valley Irrigation Canal. To look at this on the map again, this was in 2010, just prior to the beginning of the project I'm talking about. The original 1940s Topaz Bridge, the West Approach Embankment. Here we see the Portneuf River, Portneuf Marsh Valley Irrigation Canal. So all the expansion would occur in this direction to the north. So all the widening from essentially 2 lanes to 6 lanes, effectively 6 lanes, would occur with the northward expansion. And again, this had to be constrained within the existing TOA slope of the West Approach Embankment. So the final earthwork had to, as I said previously, had to have a vertical exposed face on both the north and south sides to stay within the existing right-of-way limits to the greatest extent practicable. So here we're looking from the west approach embankment. And this is the wetlands area that had to be kept as much as possible. So that meant that all the raising and widening had to occur within pretty much this existing toe slope. Quite a challenge. You're trying to turn 2 lanes into what amounts to 6 lanes and yet stay within the existing right-of-way limits, and making the embankment higher at the same time. Because of the fine-grained, weak compressible nature of the soils beneath the west approach embankment, to as much as possible, there was a desire to reduce the vertical stress increase to as close to zero as practical. And this is what we refer to in using EPS-Block Geofoam as a net zero design, meaning that after all is said and done, the vertical effective stresses on the existing subgrade are essentially no greater than that which existed prior to construction. An extraordinary challenge, to say the least, but one that has been met and satisfied many, many times now in recent decades. So certainly was not impossible. And again, had to maintain road traffic at all times, and this meant the work had to be done in 2 very distinct phases so that the traffic could be moved from one phase to another as construction progressed. So the game plan was to have a phase 1 where the road traffic would be maintained on the existing roadway and bridge, while the new westbound bridge and roadway were constructed. So again, looking at a photograph taken from the west approach embankment viewing to the east, here was the existing 2-way road traffic on a 2-lane road. In phase 1, this would be maintained, while a new 3-lane plate girder bridge was built here, and the embankment was raised and widened to the north of the existing embankment. So all this work had to be done without significant disruptions to this traffic here. Once this was done, phase 2, the 2-way traffic would be diverted to the new road and bridge that had just been constructed, while the existing bridge was removed, replaced, and the approach embankment raised for that bridge. So really an intricate choreography going on. So after phase 1 was constructed, the new bridge would be built here, the new embankment widened and raised, the 2-way traffic moved over here. Then the existing bridge would be removed, a new plate girder bridge constructed identical to the first one, and the roadway embankment raised. So, as I said, a very intricate choreography that had to be done in an area that was very remote, subject to harsh weather and shutdowns during the winter season. This was a typical design cross-section taken through the west approach embankment looking to the east towards the existing bridge. These are elevations in feet. You see just about a mile above sea level. The stationing and offsets are also in feet. So this is 3 feet, about 3 meters. I'm sorry, 10 feet, about 3 meters. So here we see with the dashed line, we see the existing embankment, and then we see the proposed embankment superimposed on top of it. This was the new access road. I didn't mention it previously, but as part of this, there was an existing access road to both the railroad. The railroad had to be able to access their right-of-way for maintenance. And also, this was the access road to some of the diversion structures for the Port Neuf Marsh Valley Irrigation Canal. So there had to be access by authorized personnel to both the railroad and to the canal control structures. So that's what this roadway down here is for, is to provide that access. This was not a public road per se. I now want to talk about the EPS-Block Geofoam that was used for the west approach embankment. The project design team, after considering all the design challenges with the soil conditions, seismic design, etc., and with concurrence of the owner, the Idaho Transportation Department, ITD, decided to use EPS-Block Geofoam as the primary earthwork material for enlarging the west approach embankment. Now, simply using EPS-Block Geofoam was in and of itself a historical first for the ITD. The ITD had never used or permitted the use of EPS-Block Geofoam for any of its roadways. And by the way, you should know this from having hopefully viewed my primer presentation on EPS geofoam, but we never ever should use the word geofoam by itself. Contrary to popular belief, geofoam is not one material. It's not one product made from that material. There are many types of geofoams. They could be polymeric or plastic. They could be glass. They could be cementitious. So it's very important to specify specifically what type of geofoam is being used. And in this case, it's block molded expanded polystyrene, what we call EPS block. Now, anytime we're using geosynthetics, and certainly geofoam is a geosynthetic, we should always follow the basic precept of design by function. And what that simply means is you need to identify what function or role you want the geosynthetic product to perform. I think it might be more than one function. In this case, the designers were looking for the lightweight fill function. There were several significant benefits to using EPS-Block Geofoam as a lightweight fill material on this project. Extraordinarily low unit weight. Most of the material used on this project had a unit weight of 1.5 pounds per cubic foot, which is a density of 24 kilograms per cubic meter. And this is a very small, this is almost 1/100th of the unit weight or density of soil. So it meant that a zero net stress design, what we call a net zero design, was feasible with only relatively modest over excavation of the existing soil. And again, this had been done many times by this point, so certainly we knew it was feasible. The other thing is that EPS blocks are inherently self-stable even when placed to have a vertical exposed face. There are some people who don't know this or don't believe this, and I'll show you a very graphic demonstration of it in a minute. The only reason you need some sort of face covering on EPS blocks in the long term is that when subjected to ultraviolet UV light from sunlight, this will cause a superficial degradation and yellowing, what we call chalking of the surface. And also you want to have some sort of acceptable architectural appearance. I mean, even though this was a remote area, you still want something that is visually pleasing. So this shows the kind of the generic cross-section of the layout of the EPS blocks. A couple noticeable features. We see the vertical face. We see that there is some over-excavation into the existing embankment, as well as characteristic stair-stepping into the existing embankment. You never just want to have a vertical face here. You want to stair-step it to basically integrate the EPS blocks, the assemblage of EPS blocks, with the existing soil in this case. EPS blocks that are placed in an appropriate way, meaning that you stagger the joints and you place them in alternate directions and alternating layers, as well as used appropriate connector plates, have proven to be acceptable even in relatively significant seismic conditions. And I'm going to show you a brief video that really, to me, is proof positive of this. This video has a lot of elements in it that I want to discuss with you. This is a full-scale shake table test that was performed in Japan in the late 1990s. In this particular simulation, the input base motion replicated that of the Great Hanshin or Kobe earthquake of 1995 that had a moment magnitude of 6.9. Now, the width of this simulated embankment is 5 meters, so about 16 feet or so, and the height is 8.5 meters, which is about 28 feet. Now, I do want to point out that the EPS blocks used here are relatively small dimensions. Again, hopefully you've watched the primer on EPS-Block Geofoam that I posted on my YouTube channel, and you know that there is no single standard size for block molded EPS. EPS block molds come in a variety of sizes, and the molds have gotten larger over time. So circa 1990s, when this work was done, the standard size blocks that were typically used in Japan, they were only 500 millimeters, about 20 inches thick. They were 1 meter, a little bit more than 3 feet wide, and they were only 2 meters, about 7 feet or so long. So these are relatively small blocks by today's standards. I just point this out because you will notice that the blocks used on the Topaz Bridge project were considerably larger in their physical dimension. So as you see, the Japanese intentionally performed these shake table tests with a vertical face without any constraint. There is no physical constraint on either side from a facing system. The only thing holding these layers of blocks together are barbed connector plates. And I point that out because there are some people in the United States, especially some academicians, who have proposed in recent years very, very complex, difficult, and expensive to construct block layouts where you turn blocks on their end and you notch them together like you're putting together some sort of complex arrangement of kids blocks. There's no need to do that. These shake table tests demonstrated unequivocally that from the simple horizontal friction between the EPS blocks as well as barbed connector plates, which were used on the Topaz Bridge project, of course, they will hold together this assemblage of EPS blocks even in a relatively significant simulated earthquakes. And again, you do not need a facing to hold the blocks together, even in an earthquake. They're quite stable under both gravity and seismic loads. Facings are only there for UV degradation long term, as well as for architectural requirements. There's a precast concrete blocks here on top. This was meant to simulate the pavement system that we'll talk about in a minute. Now, to me, the most significant outcome, well, there are a lot of significant outcomes from these shake table tests, but the most significant one is that assemblages of EPS similar to this have a very complex seismic response. You know, we know as civil engineers that typically when we design for seismic loading, we either assume that the system is rigid or it's flexible. So for example, if you had a common gravity retaining wall with a soil backfill, and you used an analytical method such as Mononobe Okaba, the wall, the backfill, these are assumed to behave in a rigid fashion. On the other hand, if you had a high-rise building, the structural engineer would design that building assuming that it was flexible, meaning that you had to consider the various modes of seismic shaking, and you had to consider the seismic amplification between the base and throughout the structure. Well, one of the outcomes of these shake table tests in Japan in the late 1990s was that assemblages of EPS blocks exhibit both types of behavior, believe it or not. For design of the pavement system up here, this system behaves in a flexible manner. So essentially, this behaves as a single degree of freedom system, meaning that here's your lumped mass up here, the assemblage of EPS blocks is your spring, and the way you calculate the spring constant is just considering the flexural and shear behavior of the EPS blocks as a beam. And the system damping comes from material and physical damping within the EPS blocks. So on the one hand, when you're designing the response to the top here, you can model this as a flexible system, and you will get some amplification. The seismic acceleration up here horizontally is greater than at the base input motion. On the other hand, with regard to the EPS blocks themselves, they behave as a rigid mass. So you use a simple P over A plus minus MC on I analysis to calculate the peak fiber stresses at the edges here, because as far as the EPS blocks are concerned, they're going to rock back and forth in this way, pounding the edges as if they were rigid. So really quite unusual behavior compared to most civil engineering structures that are, as I said, either reasonably rigid or reasonably flexible. Here with EPS fills, we have to consider both depending on what part of the system we're designing. So it's not uncommon that you actually find that the highest stresses are actually in the EPS blocks are not here underneath the pavement system, as most people assume. And certainly that's where it is under gravity loading. But under seismic loading, the largest stresses tend to be here at the bottom, at the extreme edges of the EPS mass. And the Japanese were not prepared for this. This was actually a surprising outcome for them. And in this case, because they had used EPS blocks of the same density, they actually found that the edges of the EPS blocks were pounded and crushed. Well, we now know better, of course, thanks to the shake table tests. There's a couple of documents that you can access on my ResearchGate webpage that talk about seismic designs of EPS-Block Geofoam embankments, talk about this complex, combined, flexible, and rigid behavior. And these seismic design issues are also incorporated into a large multi-year national cooperative highway research program research study for which I was honored to be a co-principal investigator. This work was done on the cusp of the 21st century, and fortunately we began this work just after the Japanese shake table tests had become available to me. I was very fortunate that the Japanese shared this information with me, as well as English language translations of their published work. So this complex seismic behavior is also incorporated into these documents. This is the overall design report, and this is the recommended standard for the EPS-Block Geofoam in highway embankments. So these documents were used for the Topaz Bridge project, the design for that, which was done around 2008, 2009. So the point is the Topaz Bridge project incorporated all of these lessons learned from the Japanese research experience with seismic loading. Also, was very fortunate that around the time that the Topaz Bridge project was being designed, 2008, 2009, the famous Big Dig Interstate Highway project in Boston. And again, I was very fortunate to be involved as a consultant on the Big Dig project. This project in Boston was wrapping up. And the Big Dig in Boston involved about a dozen EPS-Block Geofoam fills that were very broadly similar to what was being proposed for the Topaz Bridge project. Vertical sided fills, multiple lane highway, seismic design requirements. Now, the seismic requirements in Boston are more modest than in southeast Idaho, but still were significant enough. So all of what was learned on the Big Dig project, and again, here's a couple of papers discussing lessons learned and innovations on the Big Dig that can also be found on my ResearchGate website. All of the lessons learned were incorporated into the Topaz Bridge project. Now, and I should point out as well that all of these EPS-Block Geofoam fills on the Big Dig, these were all net zero stress designs. And again, that's because this part of South Boston is underlain by very significant thickness of soft organic clay. It used to be part of Boston Harbor. So I think in some places here, the organic clay approaches 100 feet, 30 meters in thickness. So tremendous settlement and stability stability issues here. So all of these were net zero designs, meaning that after this roadway is constructed, the underlying ground, in a sense, does not know the road is there. That's a rather astounding outcome, I think. I never cease to be amazed by it, even though I've worked with this now for over 30 years. That, you could build a very substantial transportation earthwork, and yet the underlying ground, for all intents and purposes, does not know that earthwork is there. So again, there was a lot of proven history with being able to do a net zero stress design for road embankments. So what I'm trying to bring up here is that the Topaz Bridge project benefited from a lot of this experience, both from the NCHRP research as well as real world experience over the course of several years on the Big Dig. And very fortunately, with the timing of the Topaz Bridge project, because I was both involved in both the NCHRP research as well as the Big Dig, I was personally able to bring this to bear as a consultant on the Topaz Bridge project. I now want to talk about the pavement system. And again, using the typical cross-section through the west approach embankment, we're talking about this cap that goes on top of the approach embankment. There are several, I think, very significant misunderstood aspects of designing earthworks with EPS-Block Geofoam. And the first one I want to address involves the pavement system. That is, what goes into the pavement system that is used above an assemblage of EPS blocks. There is a persistent urban myth, and it really is an urban myth. I can't be kind about this. This is simply an urban myth, and it seems to be very strong in the United States. I know in Western Europe, they got beyond this myth decades ago, but it remains here in the United States persistent urban myth that you need a reinforced Portland cement concrete slab, and it's usually referred to as a low distribution slab, or LDS, that's always required if you have a road or a railroad or airport runway or taxiway over EPS-Block Geofoam. There's this myth that you need to have a concrete slab between the pavement system, or as part of the pavement system, on top of the EPS blocks. I don't know how to emphasize it too strongly. This is simply incorrect. You do not need a slab. And that's not just me talking or my opinion or feeling. There are decades, literally decades of global research, and this global research goes back to the 1970s, 80s, 90s, around the world, in Japan as well as in Western Europe. There's global research as well as many case histories that support the non-use of these low distribution slabs. And this work has been published in the English language many, many times since the mid-1990s. As most of you know, in the mid-1990s, I published a book called Geofoam Geosynthetic. It was and still is the only English language book that discusses all aspects of geofoams, not just EPS-Block. And even back in the mid-1990s, I documented substantial research in Germany, in the United Kingdom, in the Netherlands, Norway, many Western European countries that show that you simply do not need a concrete slab on top of EPS blocks. Why do I emphasize this so strongly? I don't have anything against the concrete slab. I just am against bad science, or what I call a flat earth attitude. Simply people who, even though they're exposed to multiple facts, simply choose not to, they ignore the science. And again, use of the so-called low distribution slab, it's not bad per se. It does complicate compaction of the unbound aggregate layers. If you run a vibratory roller, it's like beating on top of a drum. You'll try to compact sand on top of a concrete slab, and all you're going to do is vibrate the sand. It's not going to compact. The biggest negative is the cost. We're talking about a slab that is typically at least 6 inches, 150 millimeters thick with reinforcing. This is a not insignificant cost. And if it's there just because for no good reason, you're really adding to the owner's cost needlessly. Now, that having been said, yes, there are some applications where at least a partial slab is useful for what I call road hardware. And in fact, on the Big Dig project, they used partial slabs because they connected some of the barriers to these slabs. As we'll see, a low distribution slab was not used on the Topaz Bridge project. And as we'll see at the very end, that project has been in existence for about a decade now and seems to be performing just fine without a concrete slab. Not the first time, as I said, there are countless roadways, railways around the world that do not have this concrete slab and that have been performing well for decades. So again, you should use a concrete slab on top of the EPS blocks only if you have a well-defined purpose and need for that slab. Simply using it because somebody thinks it should be there or it's a myth that it should be there is not a good professional technical reason, in my opinion. Another one of these myths is what I call the leaking fuel scenario. This is another thing that people like to pontificate about. The scenario is usually put forth is that you have some vehicle accident, involves a fully loaded tank truck, usually a semi-tractor trailer, again an articulated lorry that's carrying gasoline or some other petroleum liquid. This truck overturns, all the contents leak out onto the roadway surface, and then all of the liquid magically somehow penetrates through the impervious wearing course, either asphalt or Portland cement concrete on the surface, and percolates through all the pavement layers. And keep in mind that a typical pavement system on top of EPS blocks is about 1 meter or 3+ feet thick. So the assumption here is it's going to penetrate through all this material and then dissolve the underlying EPS. EPS is as many synthetic materials, they have pluses and minuses. And the thing with EPS that's interesting, you could put it in acids. You could put it in sulfuric, hydrochloric acid, it's not going to dissolve. But you put petroleum on it, it's going to dissolve instantly. So that's the concern here. First of all, this is never, to the best of my knowledge, in the over 50 years that EPS has been used in geofoam applications. And it's important to understand that EPS has been used in geofoam applications going back to the early 1960s, when it was used for pavement insulation of roadways and airfields. Then beginning in the 1970s, we started using it for road embankments as a lightweight fill. So there's more than 50 years of using EPS in ground as a geofoam material, and I'm not aware of any published case history anywhere in the world where this issue of EPS dissolving has occurred. Also, I mean, certainly, yes, tanker trucks do turn over with regularity. But if you look at the news, you see what happens when one of these trucks turns over is that there's either a catastrophic fire, the contents burn up. I've seen projects close to me here in the New York City area where the fire was so intense and it softened the steel girders of a bridge above it. So the steel had to be replaced. So you can have a catastrophic fire. The liquid could flow away by gravity on the surface off to the side of the road. The liquid could vaporize. So a lot of things can happen. These accidents do happen. There's a lot of things can happen. But dissolving the EPS does not appear to be one of them. Well, usually though, again, people ignore the experience and they just go with rumor and hearsay. And they typically use a geofoam on top of the assemblage of the EPS blocks. They figure, well, I'd rather be safe than sorry. The problem is you've got to be careful in areas where you have seismic design, because the interface friction between a geomembrane and overlying soil in the pavement system, or geomembrane and the underlying EPS blocks, tends to be relatively low. And in seismic shaking, you can actually have a scenario where the pavement just goes sliding off the top of the EPS blocks because of the low coefficient of friction of the geomembrane. So don't just use a geomembrane without thinking it through, whether it's necessary or not. And by the way, on the Topaz Bridge project, no, they did not use a geomembrane. The correct way to design a pavement system of an assemblage of EPS blocks, any type of pavement for road, airfield, or if you're designing a railway track system, no different than any other pavement or railway track design. But certainly for pavements, the important caveat is that you need a sufficient total thickness of material to prevent what we call differential icing in climates where this is a physical possibility. And differential icing is really the result of hoarfrost development. And it's important to understand the air temperatures do not have to be below freezing in order for hoarfrost to develop on a pavement. Let me explain why and how. Well, as we know, the interaction between the Earth's atmosphere and the surface of the Earth is very complex. You have inputs in various, first of all, heat can flow in three different ways: convection, conduction, radiation. You can also have heat transfer due to phase change of liquid water. So there's heat flowing in and out of the Earth's surface from the atmosphere depending on the time of the day. Is it sunny out? Is it dark out at night? Depending on the season of the year and areas that have seasonal temperature variation. And all of this net in and out flow, there's going to be some net heat flux into the ground. Well, this is balanced by the geothermal heat flux, and this is just the heat naturally coming from the center of the Earth. So there's a very complex interaction here. And the boundary between these two fluxes, it's not constant. Certainly in areas that have significant seasonal temperature variations, such as the Topaz Bridge site, where perhaps the extreme variation in temperature might be 100 degrees Fahrenheit between winter and summer, just as a ballpark estimate. So we're looking at, 50, 60 degrees centigrade or Celsius between seasons. This interface is moving up and down with the seasons. Well, the point is when we come along and we place EPS blocks in the ground, we're going to severely and significantly interrupt this give and take in nature between the atmosphere and the Earth's interior. And that's because EPS has a thermal resistivity that's typically about 30 times that of soil. What I mean here is that a unit thickness of EPS has the same thermal resistivity of about 30 times that thickness of soil. You want to put it into some hard numbers. If I had roughly 30 feet, 10 meters of EPS, would not be unusual for a road embankment such as the Topaz Bridge project. That 30 feet, 10 meters of EPS has the same thermal resistivity as about 900 feet, 300 meters of soil. So I think you could see that there's really going to be quite a disruption here. Well, where the disruption is particularly problematic is at night, because at night there tends to be a net heat flux from the ground surface to the atmosphere due to long wave radiation. And this is particularly significant on clear nights where we don't have clouds in the sky. Clouds tend to reflect that radiation back. So you have a clear night and you don't have much wind. Right? If you don't have much wind, you'll get more radiation as well. Well, what can happen is that because the EPS is blocking off the ground surface, it's possible for the ground surface to be substantially colder than the air temperature. And it's very important to understand, when you see, on the internet or on TV or you read in a publication, if you read about air temperature, official air temperatures are measured 2 meters, roughly 6 feet above the ground surface. So the air temperature that you see colloquially is not the surface temperature. It's measured in a shady area 2 meters above the ground surface. So it is entirely possible, and in fact there's been many, many studies going back 50 years now, at least. There's many studies have shown that under the right conditions, the surface temperature on a clear, cool night could be 10 or more degrees Fahrenheit. So, maybe 6 degrees Celsius colder than the air temperature. So you might have an air temperature that's, you think, is comfortably above freezing, but yet the ground surface will actually be below freezing. And when that happens, any humidity in the air, and there's always humidity in the air, most parts of the world, that humidity will condense and will turn from water vapor to ice. And that's what we call hoarfrost. And I'm sure most of you have seen this. All right, if you, for example, if you have an automobile or truck and you park it outside in the right conditions, and this usually happens around this time of year in the autumn, a little bit later autumn, sometimes in the spring, but certainly in the autumn. You might come out in the morning and you see that there's a thin white layer. That's hoarfrost covering the body of your vehicle. And that's because the tires on your vehicle essentially thermally insulate your vehicle body from the ground. So the vehicle body at night radiates heat into the atmosphere. The tires insulate the vehicle from the ground, so the vehicle isn't being heated by the ground. And the body of the motor vehicle gets substantially colder than the air temperature. Causes water vapor to condense, and in the right conditions it will freeze into hoarfrost. The reason I'm emphasizing this is that in the early years of using geofoams, both expanded polystyrene and extruded polystyrene, in the 1960s, they had some unexpected problems because the foams block off this geothermal heat flux and allow the temperatures here to get cold, you develop this black ice, as it's often called on a pavement, because it's clear and you can't see it. You get this black ice. And the reason it's called differential icing is that if someone, let's say the air temperature is plus 40 degrees Fahrenheit. Okay, so that would be a few degrees above 0 Celsius. So if someone were driving along a road that's on an earth embankment, you're not going to have any ice on the pavement surface. But let's say that you're going along and all of a sudden you go across an earthwork that is underlain by EPS blocks. Well, if those EPS blocks have not been designed properly, all of a sudden you're going to hit ice when you're not expecting ice. And certainly the highway department has not salted the pavement because they say, gee, look, the air temperature is above freezing. Why should we salt the pavement? And this is really where the problems come in. And I emphasize spending a lot of time here talking about this and emphasizing it because this is quite serious. People have died from this in the past, from, as I say, in the early years, the 1960s, when the first uses of geofoams, both EPS and XPS, for pavement insulation in cold climates, this differential icing phenomenon was not recognized at the time. And they did not provide a thick enough pavement on top of the thermal insulation, and there were fatalities from this. So this is a very serious issue. We need to take this into consideration. If you want to read more about this whole issue of heat transfer, and by the way, this applies to non-earth subgrade materials in general. We're talking here about EPS-Block Geofoam, but you use things like tire shreds or other non-earth materials as an alternative to soil in an earthwork. You can run into these same problems, and you need to take these things into account. I did some research on this about 20 years ago, and you can find a little research report I wrote, again, on my ResearchGate website. Now, the majority of pavement systems used above EPS-Block Geofoam earthworks use asphalt concrete as the wearing course, although sometimes Portland cement concrete is used. For example, on the Big Dig, this was done only for aesthetics because they had elevated structures, EPS fills, elevated structures. They didn't want to see what they called a checkerboard effect. They didn't want to see, a light colored pavement, dark colored pavement, back to a light colored pavement. So they made a design decision to use concrete pavements throughout. But it is most common to use asphalt pavements with EPS earthworks. And as we know, pavement systems that use asphalt concrete as the wearing course, much more dependent on the underlying unbound aggregate course or courses for structural performance of the pavement system. Right? You have to design this layer cake of a wearing course, one or more layers of aggregate. And again, just pavement research in general is over the years has shown that some type of confinement or stiffening of the unbound aggregate layers, whether the underlying subgrade is soil, EPS, or something else, is often beneficial. My personal favorite for this stiffening is to use geocells. These really work very, very well to stiffen it. Alternatively, you could use geogrids, geotextiles, other metallic elements as tensile reinforcement. I know there's been some research in Europe some decades ago where they used soil cement. This certainly works. It's just a little bit more effort. So the bottom line I'm getting at is generally when you use a pavement system above EPS blocks, some sort of geosynthetic stiffening or confinement is usually a good idea. Now on the Topaz Bridge project, they used metallic elements as tensile reinforcement, and that's simply because they were efficiently able to integrate those elements with the road hardware I'm going to discuss in the next section. Well, in this section, I want to discuss what we call road hardware, or sometimes in other English-speaking countries, they call this street furniture. And in this category, there are several essential elements that affect design, safety, operation, maintenance. One is lateral confinement of the pavement system. You don't want the pavement sliding off the side of the roadway, especially when the sides are vertical. You need safety barriers, at least along the edges of the roadway and perhaps along the median as well. Depends on the design choice. Need to provide for surface drainage, signage in some cases, and roadway lighting in some cases. Now these first two items, the lateral confinement and the safety barriers, these are particularly important when you have an EPS-Block Geofoam embankment with vertical faces as on the Topaz Bridge project. So here I've just shown you generically the road hardware locations. You need to confine the purple colored pavement system and also to provide some road barriers for safety. Now, as it turns out in Topaz, they did not use a center median divider. So what did they do on the Topaz project? The lateral confinement. They use gravel-filled gabions as a mechanically stabilized earth wall with wire mesh reinforcement, and they simply extended this reinforcement across the full width of the roadway. So here you see the assemblage of EPS blocks. No facing system is on here yet, and here you see the gravel-filled gabions with wire mesh reinforcement inside and extending across the full width of what is essentially a 6-lane roadway. So essentially, this is actually a very clever design. They were able to use the wire mesh reinforcement not only for these gabions as a mechanically stabilized earth wall, but also to provide reinforcement of the pavement system. So it was a very efficient, clever design in this case. For the safety barriers, they use jersey barriers, and in some places these are called K-rails. They used precast concrete jersey barriers only along the edges. They did not use them along the center medium in this case. And these were secured into the gabions. Right? So these had foundations that were embedded into the gabions. And in this case, the jersey barriers had cutouts at the bottom. And we'll see in a second, this was actually part of the drainage system. Again, you need to provide for stormwater and ice and snow melt drainage from the roadway surface. Now, at the time this project was done in the around 2008, 2009, the ITD had a policy that they did not use catch basins and sewerage on bridges and elevated roadways. I don't know if they have since changed that policy, but they did not use catch basins and sewerage, and I was told the reason was that they found that the sewers would get clogged up over time with roadway debris, sand and salt that was used on the roads in the wintertime, etc. And I can certainly understand that perspective. So what they did is they would provide cutouts under the jersey barriers, and then along the outer edge of the pavement system, and again under here are the gabions, they had a cast-in-place channel. So the roadway would be off to the left here beyond the photo. This is the edge median of the roadway. Any rainfall or snow melt from the roadway would flow through these cutouts into this channel that was cast in place. This is just cast in place concrete when the road was constructed, and would simply flow by gravity to the end of the roadway. So, and to the embankment in this case. So again, due to the crown of the roadway, water would run off to the edges, flow under the barrier, then flow by gravity, in this case to the west, to the edge of the roadway. And I'll show you later on in a photo where this drained off. Actually, it drains off. You can see a little bit down here. You can see a little bit of crushed rock down here. This is actually, this water runs along here to the west, and then eventually drains down here, and we'll see there's a catch basin in here to collect all the runoff from the west approach embankment. No signage in this case, no roadway lighting. I next want to talk about the facing system. All right, certainly when you have a vertical sided EPS-Block Geofoam fill, you need to pay attention to the facing. And facing was needed on this side for the gabions and the earthwork, the existing earthwork. This is yet another what I consider to be urban myths or misunderstandings with transportation earthworks with a vertical face that includes EPS-Block Geofoam. Again, I reiterate that a properly placed EPS blocks with connector plates or connecting devices is inherently self-stable, even under seismic loading. And it's worth watching that Japanese shake table test yet again. Okay, again, there's no facing system here confining these blocks. The only thing holding the blocks together is simply the friction on the horizontal surface between the EPS and barbed connector plates. There's no convoluted blocks, keyed into each other, things like that, as some people have been using in recent years. That just do nothing, in my opinion, but to drive up the cost of the project needlessly. But as I said previously, on a permanent earthwork, you do want to have some type of facing to prevent surface discoloration and chalking, as well as for an aesthetic appearance. Quite a variety of facing designs have been used going back around 40 or so years when vertical-sided EPS fills first were used. Just look very quickly at different ones that I've seen used. Cast-in-place Portland cement concrete, very big favorite. This happened to be a project in Chicago. Precast concrete panels, another very big favorite in the United States. Precast concrete lagging with galvanized steel H-piles. They've used this in Japan several times in mountainous areas. These H-piles are drilled into the underlying bedrock. Some type of precast block facing. In this case, this was an early project in the United States. In the western United States, they used segmental retaining wall blocks. Just off-the-shelf segmental retaining wall blocks. The blocks are doing nothing here but holding themselves up. This provides the face is nominally vertical here. As we know, the way these blocks connect, they have a slight backward batter to the face when finished. Shotcrete, exterior insulation and finish system, EIFS or EIFS, sometimes called synthetic stucco. Corrugated steel. This has been used in Norway, I know. Timber has been used in the western United States. And my favorite, just for its ingenuity, is what I call chia wall. This is in Japan. It's a sprayed-on vegetation. For whatever reason, either precast or cast-in-place Portland cement concrete panels have long been the norm in the U.S. Again, I don't have anything against them. It's just they come at great expense. As part of doing the NCHRP research about 20 years ago, we got actual project bid costs on several projects in the United States, including some very high-profile interstate projects that I won't mention. So using actual bid numbers from actual projects, in more than one occasion, I've seen where the cost of the facing system is the same as the cost of 4 or 6 lanes of EPS blocks between the facing, which to me is I don't know, is ridiculous. And the reason is that generally when you have these concrete panels, they're fairly quite thick. They can be anywhere to maybe 6 to 12 inches thick, so 150 to 300 millimeters thick. And if you think about it, the whole reason you're using EPS-Block Geofoam is because the underlying soil is typically soft and compressible and weak. Well, if you go to put a very heavy concrete panel there, the ground can't sustain that. So what do? You need a deep foundation system. I know on the Big Dig project in Boston that I was involved in, when we were looking at facing systems initially, they were coming up with these precast concrete panel designs on drilled shafts that were over 100 feet long. Nothing short of ridiculous. You have this EPS-Block Geofoam road embankment that exerts zero stress on the subgrade, and yet you've got to go to a very expensive drilled shaft foundation just to hold up the facing. That's doing really nothing other than to have something nice to look at. To me, that makes no sense. People do it anyway, but it makes no sense. So again, I have nothing against concrete panels. It just is, there's very hard data on more than one project to indicate this adds a tremendous expense to the overall project. As I said, I've seen projects where the cost of the facing was the same as the cost of 6 lanes of EPS blocks. So some type of facing that is supported directly on the assemblage of EPS blocks is really the preferred alternative, in my opinion. There's really 2 alternatives that have been successfully used in practice. One is shotcrete, and this dates back to the late 1970s, circa 1980. And the aforementioned exterior insulation and finish system, EIFS, or sometimes called synthetic stucco. Now, there's considerable design variability with both, especially with the EIFS, in terms of the appearance and color of the final product. With EIFS, I mean, you can make EIFS look like anything you want. You can make it look like cut stone. You can make it look like wood. You go to a lot of these amusement parks like Disney World and places like that. You look at Cinderella's castle and you think it's made out of rock or something like that. It's not. It's got EIFS as the facing system that's made to look like rock. So you can make it look like a lot of things. Now, both these systems were used on the Big Dig about 20 years ago, and there the aesthetics of the project, it was a very high-profile project in downtown Boston. Aesthetics were very significant consideration, and the designers wanted appearance of cast concrete, and were able to achieve both with both shotcrete and EIFS. This is a photo on the Big Dig about 20 years ago showing the use of EIFS panels to simulate precast concrete. And these panels, as you see here, are this is a piece of EPS that's about 2 inches, 50 millimeters thick. The EIFS system has a reinforcement layer that's either polymeric plastic or perhaps glass fiber, has an undercoat and a finish coat to give you whatever color and finish you want. And here, the color and finish was that of cast-in-place concrete, smooth cast-in-place concrete. And that's why you have these cutouts to make it look like concrete panels. So these are just thin panels of EPS that are glued to the face of the assemblage of EPS blocks. The best photo I could find at the present time was online with Google. This is a lot of vegetation has grown in the almost 20 years since this was constructed, but you can still see this is basically the same roadway. Almost 20 years later, these panels still more or less look like cast-in-place concrete. So this is certainly performed well. And as I said, there was a nice magazine article written about 10 years, I'm sorry, almost 20 years ago now, that shows how they were able to have shotcrete where with a two-layer application system, they were able to get a final look that looked like cast-in-place concrete. So my point is that if you have a high-profile project where aesthetics are a priority and somebody wants the look of cast-in-place concrete, the point I'm getting at is you can achieve this without cast-in-place concrete. You can either use the EAF system or you could use shotcrete. Both of these are fairly thin layers. You can see here, they're supported directly on the EPS blocks. You don't need a fancy, expensive, deep foundation system to hold it up. The assemblage of EPS blocks is holding up its own facing. Now on the Topaz project, they used ordinary shotcrete, which has a rough texture. But the real innovation on this project was they colored the final layer to harmonize the appearance with the natural surroundings. And to the best of my knowledge, that was the first time that any EPS-Block Geofoam project in the world used colored shotcrete. And you could see the kind of like dark red maroon, almost brownish color here. I'll show you a photo at the very end of the project, and you can really see how nicely this color blends in with the natural surroundings. So the designers here, even though this was a rural area, they were not ignorant to visual aesthetics. They were willing to live with the rough shape of the shotcrete, but colorized it to harmonize with the natural surroundings. As I said, this was the first documented use of colored shotcrete on a geofoam project anywhere in the world. I'll show you a photo a little bit later on where you can see the contrast between the colorization and normal concrete color. Well, the final design issue to talk about is extension of the Portneuf River culverts. The beginning of the Portneuf Marsh Valley Irrigation Canal is just north of the project site, so actually it diverts most of the flow of the Portneuf River. But there still is some residual flow of the river that goes underneath US Route 30 right away through culverts. So here's an aerial photo. This is that shows you this is actually at the present, but worked for our purposes. Portneuf River again flowing from east to west, and here's US Route 30 here. Just north of the project site, you have a series of flow control structures. You can see them, 1, 2, 3, 4. This is the major one. This is the beginning of the Portneuf Marsh Valley Irrigation Canal. And you could see that here's the width of the river here. Here's the width of the canal. Most of that flow from the river is diverted into the irrigation canal. And what is left in the river is much more modest. All right, so here's the remnant of the Portneuf River. And in the original 1940s relocation was accommodated by corrugated metal culverts, as I showed you previously. I showed you this photo previously, where you have culverts under the existing embankment. So the widening required extension of these culverts and the creation of new head walls on the north side using shotcrete. So the culverts had to be extended to the north again, because all the widening occurred to the north, upward in this photo. The culverts had to be extended and required new head walls. Well, I now want to talk about the actual construction. And here I've divided the topics into not technical, but really more by time. and the different phases of construction. And I also have a discussion of quality assurance, which is always very important. Well, let's begin with the 2009 construction season, some of the early site preparation work that was done. Again, as a starting point, I'll show you a slide that I've shown now a couple times. This is the view to the east from the west approach embankment. See the railroad, Port Neuf River. And the 2009 construction season included installation of drilled shaft foundations and support elements, piers, abutments, things like that for the new westbound bridge in this area. Also extension of the Port Neuf River culverts over here. And this photograph was taken during this stage of construction, 2009. Here you see the new head walls for the extended culverts. You see the wire. Use gabions here as well, as you can see, gravel-filled gabions as the head wall, and then would place shotcrete on for the facing. And you can see in the background here the piers, columns, piers, abutment for the new, what will be the new westbound bridge. Again, this is essentially effectively a 3-lane bridge. It has 2 travel lanes and a full breakdown lane. And you see some earthwork going on around here. Eventually, as noted, there'll be a new access road so that railroad personnel and canal personnel, irrigation canal personnel could get down to these facilities. For our purposes, really, the Phase 1 construction, 2010 construction season was the most significant. And again, what the Phase 1 construction involved was the completion of the new westbound bridge here and the raising and widening of the embankment. And again, the goal was to essentially keep the embankment within the toe of the original embankment while allowing for a relocated access road down here. Most of the EPS block placement was performed during the latter part of the 2010 construction season. And rather remarkably, the EPS block molder that supplied the project was located 1,200 kilometers, 750 miles from the project site. This is not a typo. Yes, there was a closer EPS block molder, but this was the block molder that was selected by the contractor. I'm not sure if people keep track of these things, but in my mind at least, this has to be a record for the distance between an EPS block geofoam project and an EPS block molder, at least in the United States. I mean, this is really a rather extraordinary distance, for reasons I will get to in a second. First of all of the blocks over this distance were hauled in flatbed semi-trailers. Again, what are called articulated lorries or Arctics in other parts of the English-speaking world. And you'll note in this case, the project was supplied using what are colloquially called meter blocks. Again, there is no standard size for EPS blocks. Depends on the manufacturer of the mold and the size of the mold that the block molder purchases. But certainly there has been a trend over the decades to making larger blocks. And the molds used for these blocks are typically 1 meter by 1 meter in width and thickness, and they can be as much as 8 meters long. All right, this is a 8 meter long, roughly 25 foot long block. that has been molded is in temporary storage prior to processing and shipment. Now, although you may mold a block this long, you certainly would not use a block of this length on a geofoam project. You typically cut this into a block that was perhaps 4 or 3 or 2 meters long. Now, you have to be careful, well, just in terms of quantity, the quantity of EPS is fairly modest, about 22,000 cubic yards, 17,000 cubic meters. Certainly not the biggest project that's been done, but when you consider the distance that's been hauled and the fact that this required over 300 truckloads of blocks, you could see that the logistics of getting the blocks to the project site were significant. And here you see the contractor had a temporary laydown area just to the west of the project site. As you'll see in a later photograph, the US Route 30, the existing 2 lanes are over here. This was the temporary block storage and laydown area that the contractor was using. Very important when you ship EPS blocks in an open trailer like this that you use edge protectors. These are molded plastic edge protectors because you want to avoid this. You do not want this to happen. Of course, you have to strap these blocks down. But at all the corners up here, you want to have these edge protectors that all truckers have who do flatbed hauling. This is to be avoided at all costs. I cannot emphasize strongly enough, and I will do it several more times before this presentation is over, that you don't want to crush or break away or poke holes into EPS blocks. For the simple reason is you're taking away from its strength. It's important to remember that EPS blocks are typically about 98% voids, 2% solid polystyrene. Here in this photo, that's about 18 times enlargement. This is a typical piece of pre-puff, as it's called. And you see the thermally fused contact between pre-puff. This is what, if we were to look inside an EPS block, you could see the little pieces of pre-puff, the little spheres here on the surface. This is what it would look like inside the EPS block. These are thermally fused together. And if we were to enlarge it about 300 times, this is what we would see inside of a piece of pre-puff. Now, of course, EPS is amazingly strong and stiff given its mass or density. But all of that remarkable stiffness is dependent on maintaining the integrity of these honeycomb cells. When you do things like this and you crush and destroy these cells, there is no way, there's no process, there's no material that can be used to patch or restore the EPS. You know, it's not like other engineering materials that if you break or put a dent in it or something that you could do things to perhaps patch it, make it almost as good as new. You simply cannot do that with block molded EPS. I emphasize that because there's no shortage of bad practices. I'll show you some towards the end of this presentation. But you know, you might say, well, it's just, I'm just crushing one corner. Yeah, but you crush this corner, you crush that corner, you break off this edge. All these little defects add up, and you're in small pieces. It's like it's the phrase, death by 1,000 cuts. You are compromising the integrity of the overall assemblage, final assemblage of EPS blocks by all of these little damages. Here we see an early stage of construction. Contractor on this project really did, I think, overall a very, very nice job. A lot of good practices to be learned here. So here's the existing west approach abutment. Again, there's still two-way traffic up here, but you see that this is protecting, well, the vegetation's been stripped away. And as we'll see, there are stair steps cut into this slope. Here we see the new westbound bridge nearing completion here in the background. Here's the bridge support elements. Here's the plate girder deck up here. Here's the railroad back here. And the canal, the Marsh Valley, Portneuf Marsh Valley Canal is down here. First of all, when you start an EPS-Block Geofoam fill, you want to have a nice, smooth, clean, dry surface. Here you see some modest over excavation. This is part of the net zero design. The contractor used generally a sand-sized material here. I believe this was a crushed basalt, hence the dark color. But smooth, level, nice, clean, dry surface. Very, very careful block placement. If you don't get started right with a smooth starting surface and get those first layers in nice and level, you're doomed to failure. There's no way you can easily correct for errors as you come up. The sequence of photos, I'll just show you how they moved the blocks. Again, they had been brought in by trailers. Here's the existing US Route 30 here, the existing 2-lane traffic. And here's the block storage and lay down area just to the west. All right, so it's behind the photographer in this view here. All right, so they had a front end loader, carefully lift the blocks, bring them down here where they had a backhoe with a scissor lift attachment on it, would carefully lift the block into place. A lot of good practice going on here in this sequence of photos. At all stages of the work, the contractors, personnel are really doing a fantastic job, I think, to maintain the integrity of the EPS blocks. There's no shortage of photos showing you people carrying these blocks by shoving screwdrivers into the side and carrying them like they were carrying a log or something like that. Those are all bad practices. You really want to maintain the integrity of all the edges and corners of these blocks as you're placing them. Notice a nice, clean, organized surface, working surface, a safe working surface. All right, personal protection, things like that. I'm emphasizing these because I'll show you how to do things badly later on. Again, all of these efforts are to maintain the integrity of these little cells, these flimsy little cells that you see here. It's rather remarkable when you think about it. These flimsy little thin polystyrene cells are what's going to hold up interstate type road traffic, can hold up trains, can hold up airplanes, but they can only do that if you maintain the integrity of these cells at all times. Okay, later in the 2010 construction season, you see the embankment starting to come up out of the ground. You see the stair steps that have been excavated into this is the existing west approach embankment. Very fortunately that this was a fine-grained soil, so there were no stand-up issues with the soil. And also, as I said, it's a fairly dry climate, so that certainly helped in this case as well. Any gaps between the blocks and the existing stair step are filled with sand. They should not be filled with water bottles, coffee cups, paper wrappers, beer cans, and other debris as you often see on American construction sites. Again, you see the new westbound bridge here in the background. See a little bit of the truss bridge over here, the existing truss. You see the new westbound plate girder bridge here. You also see that bridge over here. And again here, you see I've showed you this photo before, the EPS blocks with the gabions and the rails in place by the end of the 2010 construction season. Just to look at other aspects of the project, if we take a drive, if you will, across the existing roadway in the 2010 construction season, here you see them maintaining traffic. Actually, they had some temporary single lane traffic going on here just over the bridge itself. Here we're driving through the existing truss bridge, and you really see the new roadway surface is going to be up here. It's at least a couple feet, at least 6-7 feet, a couple meters higher than the existing roadway. So here's the new roadway surface up here. You see why the embankments have to be raised. You see the depth of the plate girder. I forget the depth of the plate girder, but I think it's probably about the better part of 10 feet, 3 meters, my recollection. Again, progressing across the bridge, you see how much higher the new embankment bridge is compared to the existing roadway surface. And this is this is looking back toward the west. This is the existing bridge here. Here we see the new east approach embankment. And again, they were able to raise this using soil because there's no soft ground under here. The basalt bedrock is fairly shallow, so this was all just soil construction. This is the new, very short, the new elevated east approach embankment, the new roadway, westbound roadways up here. Another view looking here, we see the new westbound plate girder bridge. Again, my recollection is this is about 10 feet, 3 meters deep, I think. The new widened and raised eastbound approach embankment. You see they did use some gravel-filled gabion walls here because you have the railroads right down here. You have the railroad right away, so they had to keep the embankment off the railroad property, basically. So you see the geometry required some new MSEW, mechanically stabilized earth walls here. But this is all pretty simple construction. Just again, there's no soft ground under here. Basalt bedrock's quite shallow, so and you do see the mountains rising to the east. So you get a sense of the mountains relative to the Port Neuf River Valley that we're in down here. Here you see the new head walls for the Port Neuf River culverts. You see the shotcrete's been placed. And again, the embankment coming along here. So by the end of the 2010 Phase 1 construction season, the basic new westbound right-of-way was complete. Right, this is the roadway at its final height. Here's the new bridge here. Here you see the end of the earthwork here. So this, I put together this panoramic of several photos to try to show you the entire west approach embankment towards the end of the 2010 Phase 1 construction season. See the gabions on top. The new access road is down here. There's another view at the start of the winter 2010-2011. And you could see that the traffic now has been diverted from the existing roadway to, just before the cold weather set in, they were able to pave what would be the new westbound roadway. So this roadway is now handling 2 lanes of traffic, one in each direction. Over the new bridge, the new and improved enlarged west approach embankment here. So all the traffic's now been diverted as planned. No traffic on the old bridge. You'll note that through winter 2010-2011 that there's no facing placed. And you'll actually see in this photo the face of the EPS block starting to yellow and chalk. Again, keep in mind these lower levels of blocks especially have been placed several months earlier. These photos were taken in, I think, December, as I recall. So these blocks have been placed several months earlier, and it only takes a few months for, and again, this is a northern exposure, so it does not get a lot of direct sunlight. Okay, we're looking at the north face of the embankment. So in the northern hemisphere, there's no sun on the north facing anything. But even without a lot of direct sunlight, you see very characteristic, this chalking will develop, as I said, just in a matter of a few months with EPS. But it's just really a superficial degradation. It doesn't burrow into the fill or anything like that. And just before the really cold weather set in, they were able to remove the original 1940s bridge. Here you see it lifted out of the way to close out the 2010 construction season and Phase 1. Now the Phase 2 2011 2011 construction season. Again, by 2011, there is a new plate girder bridge here. The embankment's been raised and widened. All the traffic is now here. So for 2011 in phase 2, the goal was this bridge is now out of the way to build the other 3-lane plate girder bridge and to raise this little piece of embankment here. For the purposes of this presentation, the primary element of note for phase 2 was the shotcreting of the faces of the west approach embankment. And really, the shotcreting was the foundation for it, no pun intended, was laid the prior year during the EPS-Block placement. It was a combination of judicious placement of the barb connector plates and a very careful, meticulous placement of the EPS-Blocks. So here we see the barb connector plates, and these were fairly standard galvanized steel plates used in the U.S. These are typically 4 inches square. So about 200 millimeters square. I'm sorry, 100 millimeters square. And on the exposed face, the contractor left this little lip of the plates hanging out. You see it better in this photo. Right? All of these are just sticking out here is just the edges of the barb connector plate here. Notice how very carefully these blocks are almost perfectly in alignment. All these faces line up. And this is another view looking in the other direction. You see the barb connector plate sticking out, a little bit of the plate. And you see really attention to detail when these blocks were being placed to keep this face as smooth as possible. And again, I'm emphasizing this because I'll show you a photo later on of how not to do things. So the purpose for leaving this little lip here was that in the 2011 construction season, it was very easy to attach wire mesh reinforcement. That would be the embedment underlayment for the shotcrete. That's the whole reason for leaving this little piece sticking out as a place to tie off the wire mesh. So here we see the sequence of shotcreting. This again, a photo from the end of the 2010 construction season, no facing. Here we see facing progressing during 2011. Here you see the wire mesh now attached along this section here. And in this section here, the first layer of shotcrete, just normal colored shotcrete, has been placed. The second colorized layer has not been placed yet. So we went from this to this to this, and then finally by the end of 2011 to this. This is the final appearance. And you can see, I've showed you this photo before, but to show you the drainage trough that was cast on top of the embankment. Here I'm showing it to you to show you the difference. This is what Portland cement concrete looks like, the typical light to medium gray of normal concrete without any color added. This is what the colorized shotcrete added to it. So you can really see there's quite a bit of color difference. And again, this was really a very innovative part. Very easy to do. Very innovative, though. Very clever, I think. Some additional views in 2011 of the finished shotcreted west approach embankment. Here's the abutment for the new westbound bridge here. Here we're now looking to the west, and this ground surface slopes up and the embankment ends at a point down here, back here. Another view. And I highlight this person here. This was one of the senior project design engineers on the project. He's a very tall gentleman. My recollection is he was about 6'6", so about 2 meters tall. So very interesting human ruler, if you will, or human scale, to give you really an idea of the height of this embankment at its greatest. I mean, even taking into account proportion and everything else. If you keep in mind that this person is about 2 meters tall, if you scale that up. And as many times as I've done this in my professional career, I still continue to be amazed that with these so-called net zero stress designs, that despite the very significant height of this embankment, and the pavement system and the gabion-filled wall on top, despite all of the weight, if you will, of this embankment, the underlying ground, for all intents and purposes, is not feeling any stress increase compared to what it felt for about 40 some odd years between the time the original earth embankment was built in the late 1940s and this work was done in 2010, 2011. So pretty remarkable in my mind that essentially this entire very significant embankment is just floating on the existing ground. The ground doesn't even know it's there. And there's one last photo. This is just to show you, this is now, as this what we're looking at is the point all the way back here where the West Approach embankment begins and ends. And this is really to show you how this is the new access road that will come down here. You can see that has been now graded. All of the surface water collected on the bridge that drains through these Jersey barriers into those gutters flows by gravity here, comes off the end here, flows over this crushed rock and into this new catch basin here, where it is allowed to either evaporate or seep into the ground. So that's the entire drainage system for the bridge. There's no catch basins, there's no sewerage, just this open channel that carries all the water down here. And this is all the north face of the embankment, which is, of course, the very significant side. If we look at the south face of the embankment, that had much shorter height, because the ground surface here was much higher naturally. This is just to show you that the same colorized shotcrete treatment was done on the other side. And you'll notice here, these are just expansion joints that have been cut into the shotcrete to control. Again, this climate probably has an extreme temperature variation of about 100 degrees Fahrenheit, maybe 60 degrees Celsius during the course of a calendar year. So there's going to be expansion and contraction of this shotcrete. So to control the cracking, there were contraction joints that were cast into the shotcrete. Now again, in this case, the very rough finish of natural shotcrete was tolerated, but as they pointed out to you, the Big Dig project showed very unequivocally that with some effort, you could get a smooth finish face to the concrete that looked like cast-in-place concrete. That was just deemed to be unnecessary here. The rustic look and the color was really quite enough, I think. I want to address quality assurance. I feel very strongly about this subject. And that's because trust, hope, and luck, in my mind, are not rational strategies in engineered construction. And I don't mean to be facetious here, but I've seen too many times, especially on smaller projects, that everyone says, well, it's a small project, I'll take the contractor's word for it, or, the owner doesn't want to spend money on inspection, that sort of thing. In my professional experience, if I look at problems I've seen on construction projects, some of the smallest projects have had the biggest problems, and that's simply due to lack of quality assurance. In my opinion, a robust program of manufacturing quality assurance, so in this case of the EPS blocks, and construction quality assurance, how they're placed, etc., by an independent agent who's really working for the project owner, is always required, no matter the size of the project. It's important to understand quality assurance is not the same as quality control. There is, I know there's people who use these terms interchangeably, but in engineer construction, they are not the same. They are distinctly different. Quality control is things that either a manufacturer or construction contractor does internally to check quality. So for example, with regard to the EPS blocks, yes, the EPS block molder in Kent, Washington, they had their own manufacturing quality control process in their plant. Okay, they had their own internal quality control metrics that they test for as the EPS blocks are being made. But independent of that was manufacturing quality assurance at the project site by a testing lab working on behalf of the state of Idaho. So that's the distinction here. The relevant QA activities for the geofoam are there was an on-site lab that did random sampling of EPS blocks. So the contractor was told ahead of time, look, we are going to, at our discretion, we're going to take one block out of every so many blocks, out of every so many cubic yards or cubic meters of EPS you deliver to the project site, we will take one of those blocks for testing. You don't tell them ahead of time. That was decided when a truck arrived at the project site. So there was random sampling of the blocks and testing of specimens cut from those samples. Now, although the blocks may have been sampled at random, where you cut test specimens was not at random. There's well-established places where you should take samples within an EPS block, and that's because when you mold an EPS block, it never, and I say never, will have a uniform density or unit weight. You know, when I talked earlier about the blocks on this project having an average unit weight of, say, 1.5 pounds per cubic foot, or an average density of 24 kilograms per cubic meter, that was an average for the entire block. That's 1 meter by 1 meter and perhaps 2-3 meters long. It's simply the nature of block molding EPS that you're going to get density variations within a block. You know, it's like when you bake a loaf of bread in an oven. You know, when you take out that loaf of bread, the edges of that bread are going to have a brown crust, whereas the inside of that bread is not going to be as baked to the same degree. So it's kind of the similar thing. When you bake anything in an oven, you're never going to have a uniformity of the product. And it's the same thing with molding EPS blocks. So there's a rhyme and reason for taking them at these locations, and the rationale is given in some of these publications I've referenced previously. You can find on ResearchGate. Here you can see a block at the project site where a sample has been cut at the desired location. And here in a trailer at the project site, the lab technician is using a hot wire apparatus to precision cut little cubes for testing that are 2 inches cubed, 50-millimeter cubes. These are some little beams or planks that are cut for other types of testing. And here you see one of these 2-inch 50-millimeter cubes being tested in uniaxial compression. Now again, I said the construction contractor did a nice job on this project. Well, the testing lab did a nice job as well. Notice here that they are using a machine and a load cell that is and test platens that have matched to the EPS cubes. Okay? We all know that electronic load cells, the precision of the load cell is a % of the load cell range. It's not an absolute number. It's a percentage of the load cell range. So you always want to use a load cell that is matched to whatever item that you're testing. And in this case, the testing machine as well, and the test platens. This is how you do it correctly. This is not how you do it correctly. This was an interstate highway project in the United States, very high-profile project in recent years. I'm not going to name it and embarrass those involved. This is a high-profile project, and this was actually, I believe it was the state did its own testing in this case. where the laboratory didn't take any of these things into account. They're using the same setup, platens, load cell, testing apparatus that they use to break concrete cylinders. Now, you do not break concrete cylinders in the same apparatus that you test little 2-inch cubes of EPS. You can, but don't expect the results to be appropriately accurate. In this case, I mean, the weight of the platens alone probably overwhelmed the EPS blocks, not to mention the fact that you're probably down at the extreme low end of the range of this load cell that was intended to be used to break concrete cylinders. Bad habit, bad practice. There was also pull-off testing of full-scale exemplars of the facing shotcrete. So before the contractor got to go ahead with the production shotcrete work, he had to do some test shots. And these chains were cast into the shotcrete, so the shotcrete could either be pulled in tension or in shear. And basically what was being tested here is the adherence of the shotcrete and the wire mesh, etc., to the EPS blocks. And these were just saw cut so that the area, cross-sectional area of the shotcrete was well defined. In summary, with quality assurance, I won't embarrass myself by trying to pronounce this phrase in French, but the same thing was said about a century later in English. Whatever is worth doing at all is worth doing well. And I certainly feel that way. I've worked with geofoams in general and EPS-Block Geofoam in particular since 1987. I've done a lot of research, I've done a lot of writing, I've been involved in many projects as a consultant. And really, it's just, you got to pay attention to detail when you're doing an EPS-Block Geofoam fill. And I've highlighted some of the positives of the Topaz project. And I highlight these not just because I was involved as a consultant in the project. To be quite honest, my involvement was during the design phase. And, I wrote a specification saying this is how it should be done. But then it was up to the state's inspector to make sure it was done. So the reason the contractor actually did nice work was not because of me. It was, well, yes, I mean, I wrote the specification, but still, my point is that the state was conscientious in their inspection. The contractor was conscientious in instructing their workers how to do things right. And everybody was on board with producing a quality product. There's no shortage of bad examples to compare this to. For example, there's no reason to allow a contractor to drive a tracked vehicle across EPS blocks and then allow them to park this backhoe over a weekend. There's no cause for this. There's no reason for sloppy work like this. This is a project, and this is the United States. This is the United States as well. Poor subgrade preparation. You can see the blocks. These lower level blocks are not even level. You don't store blocks by dumping them off the side of the road at the project site. If you look carefully at all these blocks, they all have corners and edges missing, broken out of them. I don't know what this gap in here is going to be. This block here, this block is worthless. Look at this block. It's running this way, parallel to the road, but it's got nothing but soil under it. Okay, when you stair-step blocks into a slope such as you're doing here, you always have to cantilever a block. You always have to have blocks underneath the block. You notice here, this stair step is much too deep. Okay, this stair step should have gone like this, and then come out and gone up like this. This EPS block here is worthless. And there's no way that this soil under here was compacted. So what's going to happen over time? Well, this is probably going to settle just under road traffic stress and vibration. And then this block is going to settle. A lot of bad practices going on here. Another project, very, very high, very recent, very high profile project in the western United States. I'll just point out in passing, this was a case where they insisted on using cast-in-place concrete facing. And you see what I'm sure was very expensive drilled shafts that were placed. These drill shafts are doing nothing but holding up a concrete facing that's doing nothing but looking pretty. It's not doing anything for the EPS. But look at the EPS blocks here. Out of alignment, out of face. You see, it doesn't take much trouble, much effort to carefully place EPS blocks. You get a almost perfectly smooth face. Whereas here you've got blocks out of alignment by several inches, several tens of millimeters from one layer to the other in a haphazard, random fashion. There's always a way to do it right, and there's always a way to do it wrong. And in my experience, it's a cultural thing, meaning that you need to have a good specification about how things should be done. You need to have a meeting at the beginning of a project. I know before this work started at Topaz that I went out to a meeting with the design engineers, the state, the contractor. I went out to a meeting at the project site. And we all talked about it, that this is a quality job and let's all work together to get this done. So if you said it's a cultural thing, if you set the attitude at the beginning, everybody pulls together, you can get a very nice job. If not, you wind up with slipshod work like this. And I could go on and on. I could show you lots of other examples of how not to do things, but I think you get the point. A postscript. Usually at this point, this is where most case history discussions end. Right? Most case history presentations and papers end with the end of construction and implying they lived happily ever after scenario. They show you what the design was, they show you what the construction looked like, and that's the end of it. Well, as I said to you at the beginning, I think one of the interesting things about this presentation is that this project has now been in the ground about a decade, so we could actually go do better than that. We could look at some things toward the present. Of course, in engineer construction, the end of construction is never the end. It's the end of the beginning, but it's also the beginning of the end for that structure. Right? These structures, especially highway structures nowadays, they may have a design life on paper of the order of 100 years. The actual design life, who knows how long, could be even longer. I mean, just look around, wherever you are, look around you. Think of how many things that you deal with as a civil engineer that were built 100, 200 or more years ago. Certainly those of you who may be in Europe, here in the United States, we talk about, gee, that's an old church, and it's 100 years old, 200 years old. In Europe, you say this is an old church or an old mosque or whatever, and you're dealing with things that are many hundreds of years old. So the point I'm getting at is that sometimes we don't know how long structures are going to last. It could be well beyond some theoretical limit. So it's of interest to, even though it's only been about a decade since the Topaz Bridge project was completed, it's of interest to look at what we can about the project. Well, first of all, early on in 2012, and this was a surprise to me, but when the American Society of Civil Engineers Geo Institute had their annual geotechnical Geo Congress, they used the Topaz Bridge project both for the cover photo of the conference announcement and program, as well as for the cover of the published proceedings. There was an industry award, the American Road and Transportation Builders Association, ARTBA, issued an award to the state for the project for its innovations. And I was quite honored to be one of those that the ITD, the Idaho Transportation Department, honored personally for their participation in the project. And these awards also occurred in 2012. So this was an industry award, and this was within ITD, its own awards. So I was very honored to receive an award from the state for participating in the design and construction of this project. More recently, in 2015, the Transporter is a in-house digital newsletter of the Idaho Transportation Department, and they featured a retrospective of the Topaz project. So this is very interesting in my opinion, because this is now the owner, and the owner is generally the most critical participant in any project, because they're the ones who've got to live with this project. They've got to live with it. They own it. They got to maintain it. So they will tend to be the most critical, or certainly the most objective in their critique. And in this digital newsletter, they noted that the Topaz project was still paying dividends, to quote them exactly. Some other quotes from this article: maintenance costs are zero for now. The roadway still rides very smoothly, and also commented that the foam, in this case the EPS, block mold EPS, is robust as a construction material. So really, I was very heartened when I saw this article, because it elaborates on what I've known for a long time, and others have known for a very long time, that when you do a project cost estimate, it should not just be the initial cost. You know, too many people focus on, I want to build something, how much is it going to cost to build it? That's very short-sighted, and you will very often not get the overall most efficient design. Because certainly with transportation earthworks, you need to take into account what we call now accelerated construction. Here in the United States, the Federal Highway Administration has known for some years now that very often, usually it is overall cheaper to perhaps select a design alternative that costs more, but you can build it faster, because there is a time cost to delay. Now, on the Topaz project, the delay was very modest. The state estimated that every day that the project design was delayed would cost $7,700 US per day, and that was in 2010. But there's still it's heartening to see people formally now place a value on doing things quicker, even if it costs more money, because you save money in the end. There's a time cost to delays. In this case, taking into account environmental considerations, the fact they were able to design something with a vertical face that had minimum disruption to the adjacent wetlands, and the long-term operation and maintenance costs, which certainly for the first several years, there apparently were none. So when you consider everything, not just the capital cost of construction, when you consider these other things, and the fact that these structures are going to last for a long time, this will typically favor the use of EPS-Block Geofoam and transportation earthworks in the right conditions, when you have soft ground, for example, or slope stability issues. So in summary, as was noted in this article, some investment now will produce gains in the long run. And it's very interesting to see this expressed by an owner, because, this is the These are the people who have to operate and maintain this roadway. This just compares the before and after. This is, again, I've shown you both of these before. This is the road just prior to widening and bridge replacement. This is what it looks like afterward. And you get, a gross overall look that basically the adjacent ground has not been overtly or significantly disturbed. It's still basically the same conditions we saw beforehand. You see here, this is the new access road I was talking about. This is a private access road, both for railroad maintenance personnel to get down here. They have to maintain this bridge. They have some signals here to maintain as well. And also, this is the major control gate for the Portneuf Marsh Valley Irrigation Canal. So the canal people need to get down here at times to regulate this gate. So this is not a public road per se. It's an access road for the railroad and the canal people. And again, this is the original US Route 30N Oregon Trail up here that you see. If we focus on the West Approach embankment, that's been the focus of this presentation. Enlarge this a bit. Here you can see again, these are the new shotcrete head walls for the culverts for the Portneuf River. Again, you see the minimal, in the scheme of things, really minimal disturbance to the adjacent wetlands. This is the detention basin for all the stormwater runoff from this bridge drains to the open channel on the north side of the bridge here. So it drains down here, comes down here, flows over the broken rock, and then into this detention basin that was built here. And you see on the south side there's also a channel that flows down and then off to the side here, and you see stone that's been placed on the side here. So this is all the runoff management from the West Approach embankment. It is all channel. The road is crowned, so it flows to the either side. Then on the north side flows all the way along here in that open channel, down through here and into here. If we take an imaginary drive down the road using views from about a year ago from Google, we start here. Our back is pretty much to the original Oregon Trail off here. Here you see how that drainage channel on the north side drains down, flows over the rocks into the detention basin. You see clearly the wetlands here are really thriving. So if we take our imaginary drive across the bridge, things, at least from the surface, appear to be doing well. This is now almost 10 years after construction. Some lightening of the asphalt pavement, but you'd expect that simply from sun bleaching. A little bit heavier wear in the United States, of course. This is the primary westbound traffic lane, so this is going to get more wear than this would be the passing lane. This is the traffic lane. You see the full width shoulder or breakdown lane here. And again, any of the rainwater or snow melt runs from the roadway underneath these cutouts in the Jersey barriers to the channel that's been cast into the top of the gabion wall here, and down this channel and into the detention basin. Pretty simple, but clearly efficient system. Seems to be working well. I mean, I don't notice in almost 10 years of usage. This, when you enlarge this photo, this appears to be some like straw or vegetation. Perhaps this fell off a truck. This is a very rural area. There's a lot of livestock growing and farming in this area, so it would not be unexpected that you have commercial vehicles hauling perhaps hay and things like that, where you've had some of that material blow off and collect on the side here. So now we're proceeding down the road. We're going towards the new bridge, right? Obviously we don't have the truss bridge anymore. All right, we could barely see the new bridge here, the concrete deck. Again, kind of remarkable to see that we've made 6 lanes out of what used to be basically just a 2-lane bridge with minimal shoulders. A little bit of pavement deterioration as we get, here's the bridge transition here, expansion joint here. So the bridge begins here, and so you see it's interesting. They basically made a single bridge out of 2 independent 3-lane plate girder bridges. But all in all, I mean, you don't, again, this is hard to see from this viewpoint, but you don't see any gross settling or anything like that, or gross potholing or pavement deterioration. And this is up close. This is the expansion joint. This is the end of the west approach embankment, beginning of the bridge here. And you see it's kind of interesting now they did connect it to basically look like one single bridge, even though it was built in 2 distinct phases a year apart. Again, you don't see any gross like bump at the end of the bridge as you often see, that sort of thing. I mean, everything seems to be holding up pretty well. Well, just to close out this presentation, certainly in my almost 50 years of professional practice, I've learned that successful construction projects are always the result of what I call a we, never just a me. And certainly the Topaz Bridge was no exception. There really were many organizations that collaborated over several years of design and construction to make this project happen. A lot of credit goes to the local civil engineers who, when confronted by the challenges of the West Approach Embankment in particular, were willing to look at a technology that had not been used for roadways in the state of Idaho up to that point in time. And just as much credit goes to the owner, the Idaho Transportation Department, for being open-minded. I've worked with geofoam since 1987, and I've had occasion to deal with many, many state transportation departments in the United States. And really, there's no two are alike. There are some that are very progressive. They're always willing to consider new technologies. And there's some that are very closed-minded. You know, we've always done it this way. We're always going to do it this way. This works for us. So just like individual human beings, these DOTs can be very independent and individual as well. So certainly the ITD deserves credit for being willing to consider something new. The primary contractor was Scarcella Brothers out of Kent, Washington State, a very established regional contractor. Really did a very nice job, at least from my perspective. I can't comment for the other aspects of the job, but from what I've seen of the EPS block placement, the attention to detail throughout the project, did a very nice job. And the EPS blocks in this case were supplied by Insulfoam, also in Kent, Washington. And they were certainly cooperative. They really, you know, they understood that they had to make sure that their blocks were going to be hauled a long distance. So when they strapped them onto these flatbed trucks or articulated lorries, you know, they paid attention to things like edge protectors or whatever to make sure that the blocks were not damaged in the shipment. I want to give a specific acknowledgement to 2 engineers that I worked with directly over the span of a couple years on this project. One is Claire Waite, PE. He's now retired from Terracon Consultants in Boise. Terracon was the geotechnical consultant on this project. And Claire was the engineer who originally contacted me and had never, my recollection is he had never done a EPS geofoam project before, and certainly was, he and others at Terracon were, you know, really were very, very good folks to work with in terms of, you know, listening to how to do things and whatnot. I just provided the general guidance to them, and all the specific analyses of the earthquake analyses, things like that, they did themselves. Also to James Porter, PE. Jim was also retired. In this case, from JUB Engineers in Boise, was the overall design consultant, not only for the West Approach embankment, but for the bridge and things like that. Jim was another good person to work with. So I interacted specifically with these two people and their organizations too, but Terracon and JUB Engineers really deserve the design credit for the overall project. And as I said, for being willing to consider something that was then a novelty in the state of Idaho. And they very graciously took the photos and that I've used in this presentation and shared them with me. This is the 2012 ITD award ceremony. This is Jim Porter. He's the 2-meter tall. I talked about meter blocks. Well, Jim was the 2-meter civil engineer on the project. Jim was that tall person in that one photo that I highlighted to show you the height of the embankment. So this is Jim Porter. This is Claire Waite. Unfortunately, due to logistics, I'm here in the New York City area, and the awards were out in Boise, Idaho. I was not able to attend the award ceremony. I was sent my certificate in the mail, but this is the 2012 award ceremony by ITD for those involved in the Topaz Bridge project, at least from the design perspective. A couple of other acknowledgments. Larry Johnson, PE. He was the former principal and owner of Heller & Johnson in Connecticut. Heller & Johnson was a small regional geotechnical firm. Has since been bought out by GZA Geoenvironmental when Larry retired a few years ago, or semi-retired. Larry still works for GZA. But in any event, my professional services with Terracon were actually through Heller & Johnson. So my involvement with the Topaz Bridge project was as a employee of Heller & Johnson in this case, and that was for professional liability reasons. But I worked with Larry for many years before he closed his firm and appreciated his cooperation with this. And last but certainly not least is the National Cooperative Highway Research Program, and this is funded by state departments of transportation, the FHWA, Federal Highway Administration in the United States. And I acknowledge them with my personal gratitude because to date there have been 2 multi-year NCHRP research projects involving EPS-Block Geofoam. The first one that started around 2000 involved the use of EPS-Block Geofoam for embankments on soft ground. And that was the report and standard that I showed you previously that was used specifically for the Topaz project. A couple years after that, there was another NCHRP project involving the use of EPS-Block Geofoam for slope stabilization, not necessarily in soft ground conditions, just in general. And I was very fortunate that I was a co-principal investigator for both of these NCHRP projects. So, certainly this was a classic case of your tax dollars at work. So all the tax dollars that flow to DOTs from fuel sales or whatever fund this sort of research, and the benefits of this research they certainly benefited the Big Dig project in Boston, and they directly benefited the Topaz project. And that means that you, the public that rides on US Route 30 through Topaz, Idaho, certainly have benefited from that, and I'm very grateful for that research funding in the past. I'd like to close out this presentation with my favorite photo of the Topaz Bridge project. This was taken a few years ago by ITD. If I can wax poetic here for a bit, I think it's interesting. The photo was taken from Old Oregon Trail Road, the former alignment of US Route 30N and the original Oregon Trail, and is viewing the modern alignment of US Route 30, I like to think of as the modern version of the Oregon Trail. As I look at this photo, I think of the countless Conestoga wagons that passed through this area in the early decades of the 19th century on their way to the Pacific Northwest. Only fitting, I think, that we see what can be thought of as a modern-day Conestoga wagon following the same path. But more than anything, to me, this photo illustrates really an epitome of modern 21st century civil engineering. It shows us that we can design efficient, state-of-art 21st century structures, a plate girder bridge, an earthwork consisting of geosynthetics, to meet very challenging geotechnical and structural conditions. It also shows us that as efficient as these structures are, that they are physically attractive as well. I think the use of weathering steel and the colorized shotcrete for the west approach embankment really creates an overall structure that harmonizes very well with the natural scenery and color of this area. So with that, I'd like to say thank you to you, the individual viewer. Thank you for your time and watching my presentation. I hope that you've learned a few things from it. And with that, I'm going to close things out and say thank you again.